So we're trying this new way of recording it. We'll be capturing the screen and our voices as well. But we think that might look a little nicer than trying to take a video with us in it and the screen, and it might be blurry, and this should be better. So synthesis is now kind of weird because you have to deal with carbon-carbon bond forming. Before, you were just given a carbon skeleton, and you could basically keep that same skeleton for most of the problem. Like you may have had to like open up an ether or something like that, but the carbon stayed the same. Now it's a little trickier. You're only allowed really tiny pieces. So I made this problem up. This isn't from an old exam or anything. This is also substantially easier than the ones on the exams. I just kind of wanted to do this one to get like kind of an intro out of the way. So looking at our starting materials, we have alcohols and alkenes of 2 carbons or less. Notice alkanes are not on the list. So we're not going to want to go all the way back to alkane. First thing I would do with any of these synthesis problems is make yourself a game plan. Look at those things you're allowed and figure out what you have to do. You see that you're allowed 2 carbon pieces, maximum. You aren't allowed 3 carbon pieces. And how many carbons are in our product? How many? 6. Yeah, there's 6 in there. So what's an easy way to break 6 down into pieces of 2? Divide it by 3. So we're going to cut it into 3 equal chunks. See how that works? 2 carbons, 2 carbons, 2 carbons. That's kind of a tentative game plan. We may have to change that, but I think it's really important to look at the molecule at the beginning and figure out what you're going to have to bust open throughout your synthesis. Kind of get a general idea in your mind of where you're headed. With Grignard specifically, you're going to be forming a carbon-carbon bond right next to where your alcohol ends up forming. So Grignards always form alcohols, essentially always. I think exactly always. Yeah, always form alcohols unless you do something weird with epoxides. But for our purposes, they're essentially always going to form alcohols. So we need to get our molecule to be an alcohol before we can do any carbon-carbon bond formation. So is it an alcohol? Yes, so in this case, we don't have to do anything. It is ready for us to go ahead and form some carbon-carbon bonds. And I'm just going to go ahead and show you what this is going to look like. So we're going to break this up. We're going to start with that bond on the left, immediately adjacent to the OH. That's a big deal. That bond has to form immediately adjacent to the carbon holding the OH. And we already decided in our game plan, we could break it at the left or the right here, but we decided in our game plan we wanted the left because that'll give it that piece of 2, and we want that. So we're going to have 2 carbons here on the left and 4 carbons here on the right. Which side is going to be holding the carbonyl? The 4 carbon side, the right side. Yep. How you know that? You look at your product. Whichever side has the carbon that holds the OH is going to be holding a carbonyl in your reactants. So we can go ahead and put a carbonyl where that OH used to be. In this case, it's an aldehyde because there's only one R group coming out of it. There's only a carbon group on one side of it. The other side is a hydrogen. The other side is our what? Grignard reagent, yeah. So you're going to be putting in a Grignard reagent with a carbonyl-containing compound. You can also put it in with epoxides. Let's just talk about carbonyls for now. What does our Grignard reagent look like? MgBr. Is the magnesium or the bromine connected to carbon? Magnesium. That's very important. Don't write it backwards. So the magnesium has to be directly connected. A quick little mechanism for you. So the bond between the carbon and the Mg, that's why it's so important not to mix it up. That bond is very nucleophilic, and it will come attack the back side of your carbonyl. What that does, it kicks one of those pi bonds up as a lone pair and generates a what on the oxygen? A negative charge. Yes, there's a negative charge up here on this oxygen now. What do you have to do to resolve that negative charge? You protonate it with what? H3O plus, and you'll write on your exam, then H3O plus as a separate step. Don't forget the word then. Because if you just wrote H3O plus on your arrow, people may think you're trying to put all three together in the same reaction. You want to make sure you're signifying to them that the H3O plus is a separate step that happens after the first two things react. I'm going to go ahead and erase this mechanism for now because it won't be on your exam. Let's go ahead and make the left really quick. It's not going to be too bad. How do you make Grignards? Mg and ether. You can just write the word ether. I heard Dr. Bean today say that she likes THF to go with it, but you're welcome to just write ether. That's fine. What's it going to be before that? What did we use Mg and ether on? An alkyl halide, like that. And now just Br2 and light and we're good, right? No, why no? Yeah, we're not allowed to start with alkanes. Remember that? If we did Br2 and light, like this, you would end up with an alkane. Are we allowed alkanes? No. Yeah, we're not allowed alkanes, so we don't want to do that. Also, Dr. Bean mentioned today that reaction is kind of sloppy and gives you poor yields. So she just really doesn't like that in general. Let's instead go back to an alcohol. What reagent turns an alcohol into an alkyl halide? PBr3. And that's an SN2 reaction. Do SN2 reactions work on tertiary carbons? No. So if this alcohol were tertiary, like I just changed it to, you would not be able to use PBr3 because that SN2 won't happen. Instead, HBr in ether at 0 degrees Celsius is your alternative. That's if it's tertiary. In this case, it's not. We had our primary alcohol, so we're more than fine to use PBr3. No excess necessary, none of that. We're good to go on that side. Let's look here at this side. So remember what we said, we needed alcohols to form carbon-carbon bonds. Looking at this molecule, how many carbons are in the aldehyde there? We have 4, so do we need to make more carbon-carbon bonds, or do we need to break them, I guess, if you're thinking retrosynthetically? We do, yeah, we need to break this up. We can't have a 4-carbon molecule. We're only allowed 2 carbons or less. Do we have something that we can do carbon-carbon bond forming reactions with? Is this the product of any of our carbon-carbon bond forming reactions? No, we're going to have to change it. What do we want to change it to? What are we going to want to turn this aldehyde to? Look up at the top if you can't remember. We need an alcohol, right? Remember, alcohol is the product of Grignards. So you need to get back to alcohol in order to do another Grignard reaction. Does that make sense? Any questions about that? Okay, cool. So we need to get back to an alcohol. Let's go ahead and throw that down there, where our carbonyl used to be. What reagent is going to take a primary alcohol to an aldehyde? Only a couple people are saying anything. PCC. Make sure you know all these reactions by heart. What if you use Jones on this? Jones oxidation or the dichromate. What would you get? An acid, yeah. PCC is weaker, a little more selective, and it's going to stop at the aldehyde. It won't oxidize all the way to carboxylic acid. Jones is stronger, and you end up with the carboxylic acid. So just keep that distinction in mind. All right, we're back to an alcohol. Great. Look up at the top. When we broke a carbon-carbon bond, we broke it right next to the alcohol, right? See up here at the top? That bond we broke is immediately adjacent to the alcohol. If we want to use the same method, which we're going to go ahead and do, we also have to do the same thing. We have to break the bond immediately adjacent to the OH. Go ahead and put that in red. We're going to break that carbon-carbon bond right there. There's another more elegant way to do it. We'll talk about it in a second. I just kind of want to show you this to kind of show you the pattern. So we said the alcohol is the product of our Grignard. So what two things are going to be at the bottom of the arrow if we're doing a Grignard reaction? We need what two things? We need MGBr, we need a Grignard reagent, and we need what? A carbonyl containing compound, exactly. So we're going to break that, and how many carbons are going to be on the left? 1 carbon on the left. How many carbons on the right? 3. Yep. Sorry, 3. Which side is going to contain the carbonyl? It's going to be the side that originally held the alcohol. So in this case, it's going to be the left side. See, up on our product here, the carbon holding the OH, that's going to continue holding the carbonyl at the bottom before the reaction. So we need to put that carbonyl on that left lone carbon. Does everybody see why we picked the left side instead of the right? That's a crucial piece. Cool. And then what's going to be on our right side? If we know the carbonyl is on the left, what do we got on the right? MGBr, that's our Grignard. Yep. And which element's going to connect to carbon? Mg. Yep, so it's going to be BrMg this time. So it may change depending on the way you write it on the molecule. All right, are we missing anything else? What are we missing? Then H3O+. Remember the mechanism. That bond comes in, backside attack on the carbonyl, kick that pi bond up, generating a what? Negative charge, right? So in order to get rid of that negative charge, we're going to need to add what? Yep, aqueous acid. Then H3O+. Cool, this is kind of a similar pattern, remember? Looking up here, we have a Grignard and a carbonyl compound, and then we broke those two down. We ended up here with a Grignard and a carbonyl containing compound. Let's go ahead and make the left. That's formaldehyde. We're allowed alcohols or alkenes. Can we make an alkene? That requires 2 carbons. We have 1 carbon, so alkenes are out. We have to go back to alcohol. So let's go ahead. Make methanol. What reagent are we going to use to turn methanol into formaldehyde? It's a primary alcohol, right? Or a methyl alcohol. So what reagent will stop at the aldehyde? Which reagent is the weaker oxidizing agent? PCC. Yep. Look at the pattern. Alcohol with PCC up to an aldehyde, then H3O+, you have your alcohol. Oxidize it again, make your carbonyl, another Grignard. Do you see the pattern? This pattern like this will show up on your exam. It may not be exactly PCC, or you may have to use a ketone instead of an aldehyde, or slightly different carbonyl containing compounds. But that same general pattern is going to be there throughout. So we're done here at the bottom, right? That's a 1 carbon alcohol. We're allowed alcohols of 2 carbons or less. So we're set. Deal with the right. We're going to make this with Mg and ether, which we already did. Br, 3 carbons. All right. So we have a 3-carbon molecule, right? Are we allowed 3 carbons? No, we're going to have to bust this open again. What functional group do we need to get back to in order to do the carbon-carbon bond forming? Alcohol. We need to get back to an alcohol again. Remember? So at the top we had an alcohol. Then we made this carbonyl compound. And then we said, we can't make carbon-carbon bonds when there's that carbonyl there. We need to go back to an alcohol first. And we did that. That showed up again. So we need to turn this guy into an alcohol. We're going to turn that alcohol into an alkyl halide. What are we going to do for that? What reagent? PBr3. Yep, exactly. So now we have this 3-carbon alcohol. What are we going to do with that? What do alcohols prime us for? Grignard. Yeah, that's the whole reason we wanted to go back. We need to do another Grignard. Why? We need to break another carbon-carbon bond. Does everybody see that? We can only have 2 carbons. We still have 3, so we have to break another bond. So what 2 things are going to be at the bottom for this Grignard reaction? We're going to have a Grignard and what? And a carbonyl-containing compound. Exactly. So we're going to break the bond immediately adjacent to the carbon holding the OH, right? Same as before. So that's the bond we're going to break. Which side is going to hold the carbonyl, the left or the right? The left. Yeah. Why the left? Yeah, the left side has the OH on it at the end of the day. So that's going to be the side at the beginning that had the carbonyl. So how many carbons are on the left there? 1. 1 carbon, carbonyl-containing compound. Look at that, formaldehyde. We already made that. So we can stop there. What are we going to combine with formaldehyde? It's going to be a what type of reagent? Grignard reagent. Yep, how many carbons in the Grignard? 2, exactly. 2-carbon Grignard. And I think we made this. Yep, look right there, the top. We already made that guy. So we can stop. And you're done. Any questions on this? What's up? If you already synthesized them in the problem, then you can say already made. Yes, that's totally fine. So see, on the right here, I pointed to formaldehyde and said we already made it. Look right here. So we showed how formaldehyde was made from a 1-carbon alcohol already. We used PCC down to methanol. Methanol is allowed. So we already showed them what to do. We already showed them how to make that formaldehyde. So we don't need to rewrite the recipe twice. Good question. What's up?
So whenever you need a carbonyl group, are you just going to form an aldehyde?
It'll be an aldehyde or a ketone. And that brings us to a really good point. Let's go ahead and talk about this. The degree of alcohol you use is going to change what carbonyl-containing compound you use. So if you need to form a primary alcohol, right? That's going to break the bond immediately adjacent to the carbon. So what carbonyl-containing compound is going to be on the right side? Let's go ahead and keep the same direction. At the bottom, what carbonyl-containing compound are we going to have? Formaldehyde. Yep, that is the only possibility here. Why? Does everybody see why? Looking on this side, the side that has to contain the carbonyl, right, because it's connected to the oxygen, that side only has 1 carbon on it. So are there going to be any R groups coming out of your carbonyl? No, so you're going to have formaldehyde. What about a secondary alcohol? If we want to make a secondary alcohol, again, we're going to break the bond immediately adjacent. And what carbonyl-containing compound is going to be at the bottom? An aldehyde. Yep. So we're going to have 1 carbon in with our aldehyde on this one. Or in with our aldehyde. So it'd be 2 carbons total. Sorry, that probably was confusing. It's 2-carbon aldehyde. There's going to be 1 R group on there. Does that make sense? What about a tertiary alcohol? We're going to break a bond immediately connected, immediately adjacent. So what carbonyl-containing compound do we have now? A ketone. Is everybody following? Does this make sense? Where I'm getting all of this? What's up? Oh, yeah, I think I meant, sorry, I wrote that wrong. You're right. Yep, absolutely right. Thank you. Yeah. So this will be acetaldehyde, 2-carbonaldehyde. So this one will be a ketone. Everybody see that? The piece on the left here that has the OH on it is going to be the carbonyl containing compound. How many R groups do we have on our carbonyl? 1, 2. Yeah, so 2 R groups coming out. That makes it a ketone. That makes sense? So whether you have a primary, secondary, or tertiary alcohol, that's going to matter. And this is why. That's the thing that's going to change. What's that? The same, you would use any appropriate Grignard reagent. So in this case, no, you would not use the same reagent for all of them unless I change it. I just changed one of the problems. Now the same reagent for all of them. It would just be methyl Grignard. So with all of these, you would be putting in CH3 MgBr. CH3 MgBr. Everybody see that? Because there's one carbon on the side that doesn't hold the alcohol. Every time it's just a CH3. So we're going to connect CH3 MgBr. Cool. We have about 9 more minutes. I want to go over one more technique with Grignards. This is going to be a little bit of a concept shift, slightly different reaction. Instead of reacting with a carbonyl-containing compound, we are going to react with an epoxide. That's also totally allowed. Grignards are capable of opening epoxides. So what I want to do, let's zoom in on this guy right here in our synthesis. You remember at the beginning, we said we wanted to cut it into pieces of 2, like 2, 2, and 2. Did we do that on the first way? No, yeah, we didn't do that. That's because I just wanted to stay with the Grignard carbonyl-containing compound method. That method, you can basically make any compound you want. You can keep adding carbon by carbon by carbon by carbon as long as you want. So I wanted to show you that first because that's kind of a hack. If you forget everything and you don't know what to do, you can literally Grignard on carbon by carbon by carbon just like we did, using the same repeating set of reactions. Yes, you will. Yeah, so Sabrina told me a story where someone's exam, their synthesis was like like front and back of a page, like huge synthesis, full points. They just Grignard it on every single carbon, carbon by carbon.
And they got full credit. So hey, like if you forget,
yeah.
If all you remember is Grignard, do the Grignard.
So yeah, this is the bare minimum. You have to know this sequence because that can hack you out of having to do some other synthetic techniques. I wanted to show you one more though, for the sake of elegance. So yeah. PCC. Oh, Dr. Milianic doesn't.
Dr. Milianic didn't get to that yet. So if you're in PCC and you're in this class, like don't worry. You're okay. You're okay.
Cool.
Yeah.
Sounds good. No problem. Yeah. So we said before we wanted to break it into chunks of 2. So looking at this 4-carbon alcohol, originally we broke it at the left there, giving us chunks of 1 and 3, which wasn't great because we had to then turn around and break down that 3-carbon compound. So what we can do instead, we can break it right down the middle, 2 and 2. And let me show you how we would do that. Let's go ahead and redraw our compound. So we had, that's 4 carbons and an alcohol. So what we're going to do with this instead, we're not going to break the bond immediately adjacent. This is a new technique, separate technique. We're not going to break that immediately adjacent bond, and we're not going to have a carbonyl-containing compound. We're going to break this bond. What we're going to do instead is we are going to attack an epoxide. Sorry, it's kind of a, there we go. With our Grignard. 2-carbon Grignard. What this is going to do, this highly nucleophilic bond right there between the Mg and the carbon is going to come, backside attack the epoxide, and that's going to break this sigma bond and push it up onto the oxygen. Kind of a similar deal to the carbonyl, but slightly different. You're still going to end up with a what on the oxygen, though? A negative charge. Negative charge on that oxygen once it swings out. It's going to swing out here. After this bond breaks right here, it's just going to swing open. So you'll end up with a negative charge on that oxygen. What do we do to resolve that? Protonation with what? H3O plus, then H3O plus. Not in with the reaction, so say then. So this is another target you can use for Grignard. So with Grignard, you can attack epoxides if you want to break the bond that's one bond further away. So if you're using carbonyl-containing compounds, you're breaking the bond immediately adjacent. With epoxides, you can go one bond further. You actually have to go one bond further. Don't try to do anything with epoxides where you're breaking the bond immediately adjacent. That won't work. It would be right there. I'm going to erase the mechanism arrows since we don't need that on our exam. How do we make epoxides? What's the reagent? MCPBA. And that's going to take us back to a what? An alkene. Are we allowed alkenes, 2 carbons or less? Yes, we are. Yep, so we're done with this. Set to go. This, you know how to make it. I'm not sure if we made it already or not. Did we make a 2-carbon Grignard? We did make that, so we already made that. There is one more technique that you can use, and it's using the acetylide anion. That looks like this. Triple bond, deprotonated carbon on the end with a lone pair and a negative charge. This right here is the acetylide anion. What this can do, it can attack carbonyl-containing compounds, so this ketone, for example, but it could also attack aldehydes or formaldehyde or any of that. It can also do SN2. That's something that Grignard isn't really known for, so this is a little bit more versatile. You can actually react it with this alkyl halide. This lone pair can come attack the back side on that alkyl halide and kick the bromine out. SN2 reaction. That would get you, there's your acetylide, new bond to 2 carbons. It's kind of hard to conserve the, I'm actually just going to write out structural. So we've gone from 2 carbons and 2 carbons, and we've made 4. So that's another way you can form carbon-carbon bonds. The only restriction with this alkyl halide that you need to know, it must be primary. If you try to do that acetylide anion reaction with, say, a secondary, let's go secondary alkyl halide, what's going to happen instead? So acetylide anion, it is a great nucleophile, also a strong base. So if you use it on a secondary substrate, what reaction are we now doing? E2, it's not going to be SN2 anymore. Before, on this compound below, the primary alkyl halide, we could do an SN2 reaction. Very little steric hindrance at that primary site, and that allows SN2 to happen pretty seamlessly. In the case up here, with the secondary alkyl halide, it would rather abstract a proton and form a double bond. So keep in mind that it must be a primary alkyl halide. So those 2 things we covered at the end, the epoxide and the acetylide anion, those are 2 separate, slightly more advanced techniques. I mean, slightly more advanced, I think. But this right here, this synthetic pathway, where we're just using the carbonyl-containing compounds in Grignard, will not fail you. So know this for sure. It's going to make your life easier if you know some of this other stuff. But this is the bare minimum. If you know this, you can weasel your way out of a lot. So if you're freaking out about synthesis, at least start here. It is 6:59. I'm going to turn it over to Sabrina. Take 3-4 minutes, talk to each other. If you have questions, I can come around and answer. We're just going to get this set up to do the 2017 exam. What's up? I mean, I'm not really the person to ask, but I'm sure he would think